Right, now we're just starting with the written response. So let's have a look. And we've got copper sulfate pentahydrate. This is all water of crystallization. So these salts contain water. Often you don't see this part of the formula, but this is actually, they contain water. So calculate the mass of water in a 20-gram sample. Well, let's just calculate the molar mass of 5H2O, which is 5 times 2.02, the hydrogen, plus the 16, it's 18.02. 5 times 0.02 is 90.1 grams per mole. What's the molar mass of the entire thing? CuSO4.5H2O. Well, that's going to be, get your periodic table out. Copper 63.55 plus sulfur 32.07 plus 4 lots of oxygen plus the 90 grams. Okay, let's add that up. 63.55 plus 2.07 plus 90.1, 249.72 grams per mole. All right, so what's the fraction? Calculate the mass of water. So we've got 90.1 over 249.72. So that's a fraction of water in that, and then we're going to multiply that by 20 grams. 9.1 times 20. And that is 7.216 grams of H2O. All right. All right, what's the next one? Okay, 5 grams of an oxide of phosphorus was produced. Okay, so I might zoom this in a bit. I'm just going to mark this out so I know where I'm at. Okay, thanks for that. Okay, let's get back to it. Okay, right. Calculate the mass of oxygen. So some of this is phosphorus. So 2.46 grams out of the 5 grams is phosphorus. So this is a percentage composition question. And if 2.64 grams, 46, that means oxygen must be 2.54 grams of the 5 grams. So we just got to convert these to percentage. 2.46 divided by 5, 0.492, which equals, times it by 100, 49.2%. We could minus it by 1 here, or we could just, let's just do 54 divided by 5, 0.508, which equals 50.8. Alright, now determine the empirical formula for phosphorus oxide. Right, well, how many moles of phosphorus? Moles of phosphorus equals 2.46 30.97 2.46. So moles, and let's calculate the moles of oxygen. It's 2.54 over 16. 5.75 moles. Right, now we want to find the ratio. So divide by the smallest one. Equals 1. That equals very close to 2. So that's our ratio, 1 to 2. So phosphorus dioxide is our empirical formula. In order to determine the rate of reaction, so we're going to put volume here and time in seconds. Give it a heading. Okay, so we just got to plot these points. 0, 0, 20, so that's 30, 26, 248, close to 50, 375, a bit less than 80, 400, 102, 600, 152, 176. Okay, and then they say, use the data, draw a line of best fit. That's my straight edge. See the line that best fits all these points. Oh, should use something other than a garden stake. Right, so the question is, that's a line of best fit. Identify the dependent variable. Dependent variable is the thing being measured. So that's is the volume. And calculate the volume of, well, volume of what? Of H2 gas. And calculate the rate of reaction. So rate is the slope. So rise over run at 550. So I would just pick something that's pretty close to the here, because all this slope's the same, right? So what's the run is going to be, I mean, it would work for any of these points, 300. I'm picking points that are very close to here. And so that's 102 minus 76, so that's 74. Okay. So rise over run, 4 over 300. I mean, you might get slightly different numbers in here, so that's going to equal 0.246 to 2 significant figures. 0.246, and then what's the units? Milliliter, to 2 significant figures. 0.25 milliliters per second. Significant figures. 23. Oh no, I must have had a, apologies, a printing error here. Okay, so I should have started here. Okay, kind of independent question, so that's okay. Now here we've got vinegar, so it relates to the data we're measuring the H2 gas that was given off here. State, so always look at the keywords. 3 observations. What are indications of a chemical reaction? Well, you get the bubbling. So 1, bubbles of gas forming. 2, we start off with a chunk of zinc, right? And then the zinc dissolves. The zinc metal changes. Changes size. 3. Do you reckon it would get hotter? Might get slightly hotter. Alright, there we go. 24. The element calcium exists mostly in nature as a stable isotope, calcium 40. Other types of calcium is calcium 45. Define term isotope. An isotope are elements with the same number of protons with different number of neutrons. An isotope is an element with the same number of protons but different number of neutrons. Okay, so you got to look for what they want you to do. Explain. That's one. The difference between one that is stable, one that's stable. A stable isotope has an unchanging nucleus, number of nuclei. An unstable isotope has nucleus that loses the nuclei that form of radiation. An unstable isotope has a nucleus that loses nuclei, protons or neutrons, in the form of radiation. Alright, so isotope calcium-45. So calcium-45, if you look up calcium, you can see this is, that's the average mass of all the isotopes. This one has a mass of 45. It has protons, 20 protons. So here, can you write a balanced equation for this decay process? And the key thing here is a beta particle. Beta particle is an electron. Okay, so it is going to give off an electron or a beta particle. Once you can write it like this. And electrons we're saying has no discernible mass, has a charge of -1. Now these has to be balanced. So calcium, something here with a certain number of protons must be 21. So now we look at our periodic table. Scandium has 21 protons. And it's going to have the same mass. Because all that happened was that a proton changed to a neutron. And they have the same mass. And in so doing, it gave off an electron or a beta particle. Okay, explain how Hess's law relates to the law of conservation of energy. Well, the conservation of energy says that energy cannot be created or destroyed. The law of conservation energy that cannot be created or destroyed. Now, how does this relate to Hess's law? Hess's law says that all the steps of different reactions will equal the total amount of energy as one big step. Says that many small steps in chemical Hess's law says that the energy in many small steps in chemical reaction will equal the same energy as one big step A plus B is going to equal C. And delta HA, delta HB equals delta. I mean, if you have to draw a diagram, sometimes that helps. Okay, so C, A, B. All right. So let's have a look here. Aluminium chloride can react with oxygen. Okay, so this is the target reaction, and we want to use the given information to replicate this. Now what we have to do sometimes is work backwards, and if we do have to flip one of these, we've got to reverse the amount of energy that it was recorded. Okay, so looking at this, if we start with AlCl3, that means we'd have to reverse this. So that's going to be, let's write it down. We've got 2 moles of that, so like 2 AlCl3 will give us, what's this? Double that, it's going to be 3 Cl2 plus 2 Al, and the delta H will equal positive 2 times 704.2, which is 14. Kilojoules. You're right. Now we've got that. We just have to end up with Al2L3 because we've already got the chlorine. So starting with, so we're going to, did we get Al? Alright, so here we've got Al, 2Al plus 1.5 oxygen. It's going to give us Al2L3. Now this remains unchanged. 2 minus 1.6 kilojoules. And let's cancel anything that's on both sides and doing opposite sides. Now if we add all these together, do we get what we wanted? 2 AlCl3, 1.5 oxygen, and we've got the chlorine and that. Okay, so we've got to find the sum of this, so that's delta H equals 8.4 minus 6. Okay, let's check. Right. Use Hess's law to calculate the energy enthalpy change. Right. So so we've got a bag of fertilizer. Calculate the mass of potassium. So 100 grams is going to have 48.5 grams KNO3. Okay, calculate the mass of the potassium. Well, First of all, how many moles of KNO3 do we have? We've got 48.5. And what's the molar mass of KNO3? Here, 39.1 plus 14.01 plus oxygen 3 times 16. Excuse me, technical issues here. Apologies, hang on. I'm just going to mark this out again. I need a better system here, really. Where are we? One second, sorry. Okay. Back to it. 39, calculating the molar mass. 101 of the potassium nitrate per mole. 101.11. So now, what's the number? Now, I suppose you could do this a number of ways, like percentage composition. Yeah, you'll get the same answer. Seven, 9, 6, 9, 7. Is that 4, 7, 9, 7 moles? Okay, so mass of potassium equals, so using this formula, moles equals mass over molar mass, then mass is going to equal moles times molar mass, 0.4797 times the molar mass of potassium, 39.1. 18.75 grams of potassium. Now, calculate the concentration of nitrate ions. So, what's handy, I've got moles here, is 100 grams equals 0.4797 moles of KNO3. 10 grams equals 0.04, 10 times less, 7 moles of KNO3. And nitrate ions is going to be the same, 1:1 ratio, NO3 ions, therefore 0.04797 nitrate ions moles of nitrate ions. So what's the formula when we want to know concentration? Concentration is moles over volume. We've got 0.04797 in 10 liters. And there's 0.04797. Well, actually, we just moved the decimal, don't we? 0.00479 moles per litre. is the concentration of NO3 ions. Explain, here we go, question 27. When a small piece of lithium metal is placed in water, it fizzes, catches fire. Okay, this is one of the group 1 metals that are very reactive with water. Explain the reactivity expected if similar size pieces of sodium, magnesium, potassium and rubium. So they want you to compare sodium to lithium. We started off with lithium. To sodium and then going down. So remember, they become less electronegative as you go down, which means that the ionization energy is less, meaning those electrons are easier to get rid of, like to react. So they're going to get more reactive. Explain. Okay. You might mention that. But so going down, group 1, the elements become more reactive as they as first ionization energies are less. More active, therefore more vigorous reaction expected. The metals identified react with non-metals to form salts. Something like sodium chloride, right? Identify, describe the bonding in pure metals. Compare the bonding in metal salts. All right, so pure metals have metallic bonding. Which has a sea of electrons between nuclei, where, so you got to compare metal salts, e.g. sodium chloride. Remember, it pinches the electron. Have ionic bonding. Held together by electrostatic forces. Compared with bonding metal salts. Account for the high conductivity in metal elements compared to the lack of conductance in solid metal salts. Well, metallic bonding in metals has unbound electrons that allow for electron movement, a current. Metal salts have no available electrons. Metal salts have no available electrons for electron flow. Hence, no current. Not conductive. Okay, define Avogadro's law as it relates to ideal gases. All that's saying is that all gases of a given volume, temperature, and pressure have the same number of particles. Or, yeah. Or moles. Calculate temperature of an ideal gas. Okay, so volume, pressure, molar volume, you got N equals 1. So we're starting to look like we got PV equals nRT. Ideal gas should trigger that. I'm looking for the data sheet here. On your data sheet, you've got, where is it? Up here. And we want the constant number. Where is it? Gas constant. Right, so let's just write down, what do we want to know? Calculate the temperature. So I like to rearrange this before we start. So T is equal to, now divide both sides by NR. T is equal to P times V divided by N. So let's have a look. We've got pressure 130 kilopascals times the volume of 26.5 divided by 1 times the gas constant 8.314. This is going to be in Kelvin. 130 times 26.5 divided by 8.314, 414.36 Kelvin. And that's your answer. So minus 270, so it's 100 and something degrees. Right, did we get that? Oops. Okay. Under standard conditions, reaction between bromide. So just write this out. Right. So we've got a reaction here that they're telling us. Write two half equations and the overall cell equation. So we're starting off between bromine, aqueous, Br2 plus iodine, aqueous, forms bromine, aqueous, plus I2 aqueous. So let's have a look at our standard potentials. Can we find these anyway? Bromine, Br2 aqueous. These are half equation. This is reduction. I'm just writing it as is here. Half Br2 aqueous plus E gives us bromine. Oh, that would be 2 here, wouldn't it? And this would be 2 here. Aqueous, all right, and then the other one, which is iodine. So, but we're going to do this backwards. Oh, well, hang on, before we finish here, let's put the, so 110 volt, so 1.1 volts positive. And the oxidation is iodine aqueous ion, and it accepts the electron. Well, it turns into, well, it's plus half. Now, in this case, so we're not choosing the solid, we're choosing this one here, and we're going to reverse that. So not 0.62 minus 0.62. Okay. So overall, 2 half equations overall. So add them together, the electrons cancel out. Half Br2 aqueous plus I. Yeah. And that's going to equal 1.1 minus 0.62. 0.48 volts. Okay. Getting there. Student was asked to prepare sodium carbonate solution . Okay, so design a method could follow. Okay, calculate mass of a sodium carbonate . 250 ml required. I mean, you want to explain how to do this. So 0.15 moles per liter equals 0.15 divided by 4, 250 mils. 0.15 divided by 4 moles of Na2CO3 equals 0.05 moles. Mass, moles equals mass over molar mass, and mass is going to equal moles times molar mass. What's the molar mass of Na2CO3? Have a look at your, so it's 2 times 22.99 plus 12.01, that's carbon, plus 3 times 16. So 0.375 times 2 times 22.99. Okay, times 105.99, 0.0375, so 3.97 grams Na2CO3. Okay, calculate mass of, so the method should be to weigh 3.97 grams of Na2CO3 and 2 volumetric flask. Three, and this is a 250 ml flask. Add distilled water to flask up to the 250 ml mark. Now, I mean, you could add further steps about rinsing, but I'm just for dissolve, etc. I mean, that's basically what you're doing. Okay, putting the steps down. Right, instant cold packs often found in first aid kits. One type of cold pack contains silver bag. Okay, so here's an energy diagram. So the bonds, so that's exothermic. Bonds of formation and bonds breaking. This is endothermic. Energy required to break bonds. Energy required to break bonds is greater than in forming bonds. So it requires more energy to break the bonds than it does to form. Calculate the enthalpy of solution. So heat of solution, remember Q equals MC delta T. So what's the mass? Well, the mass is 100 plus the 10. So 110 grams times 4.18. That's the constant that we're going to use. Are we doing grams or kilograms here? Let's have a look. Where is it? Okay, so if you're using kilograms, it's 4180. If you're using grams, it's 4.180. Next, I'm going to keep it in grams, 4.18. Delta T is 7 degrees. Okay, so let's try this. Three, two, 3218.6 joules. Okay, so this is the heat given off. Now the heat of solution wants the joules per mole. So this is 3.2 kilojoules. Okay, so now how many moles of solute did we use? 10 grams. What's the molar mass of NH4NO3? Oh, I've got to get. Okay, so it's nitrogen 14.01 plus 4.04, the hydrogen plus 14.01, nitrogen plus 5 times 16, the oxygen. Okay, let's just try that. 14.01 plus 4.04 plus 14.01, 5 times 16, 2.06 grams per mole, 112.06, 10 divided by answer, 0.089 moles. Okay, so heat of solution is 3.2 kilojoules. 89 divided by 9. So that's roughly 35.955 kilojoules per mole. Let me just double check that. Oh, that's a 3. Sorry. 0.01. Down 16. 80.06. That's 12. Sorry, 0.1249. 0.1249. 3.2 kilojoules divided by 0.24. 25.8 kilojoules per mole. Activation energy for this reaction is 31 kilojoules. Use the axes to draw an appropriate enthalpy profile diagram. I mean, let's assume there's 10 each. So let's start here. Okay. Now they're saying the activation energy, that's the energy required. It's going to go up 10, 20, 31. Let's go up to here. Now the all right, okay, so this is endothermic. So it's going to end up here somewhere. and roughly 10, 20, 25. Okay. Calculate. And so we're going to label this enthalpy change. 25.8 kilojoules, 31.2 as energy of activation. Enthalpy good X. Like that. Calculate the change in Gibbs free energy for the dissolution. So think of that formula. It's on the sheet as well. Delta G is the enthalpy minus the temperature times entropy. Okay, now be careful because entropy is in joules. And we've got this in Celsius. So temperature we've got to convert to Kelvin. 25 plus 273.2. 298.2. Okay, and we'll write this as kilojoules, which is 0.10875 kilojoules. Delta H from the previous page. Always write down what you know. 25.8 kilojoules. The Gibbs free energy is going to be 25.8 minus 298.2 times 0.1875. 25.8 minus 2 times 0.1875 minus 6.629 kilojoules. Okay, so now because Gibbs is negative, therefore negative Gibbs means spontaneous. Spontaneous reaction. Okay, you got to remember to read the question. All right. Solution of hydrogen peroxide will quickly decompose into water and oxygen in the presence of manganese dioxide reaction. We did this in class. Draw a graph consisting of what happens when the manganese lowers the activation energy. That's what catalysts do. Okay. So the reaction proceeds much quicker. Okay. Explain in terms of collision theory how the rate of decomposition is affected by temperature. What happens with increased temperature? Increases particle motion. Speed. More collisions occur. The rate of reaction increases. So we've explained H2O2 decomposes faster at a higher temp. That's why we keep it in the fridge. Outline how spectral evidence was used. Well, to propose a Bohr model of the atom, and how is this model changed by Schrödinger's view and the nature of electrons? Well, the Bohr model, that's where you've got the protons and neutrons in the nucleus, and then you've got different electron shells, and when you have a photon, hits an electron, it can jump up at discrete energy level for a moment, and then when it drops back down, it gives off a photon of discrete energy, resulted in spectral lines. So you've got the certain elements have spectral lines, which spectral lines these spectral lines are evidence for the electron shells. Okay, how this model changed with Schrödinger. So this sees electrons as particles. Schrödinger showed that electrons have wave properties. Okay, like this. Does it say? Doesn't say to show evidence for this, so you could look at the diffraction of electrons as evidence. Okay, but of the electrons having wave properties, and the electrons and had orbitals, regions of probability. So this, you could draw a diagram. S&P shells and subshells. Hence a new model of the atom. When solid sodium hydroxide dissolves, the temperature rises. However, when solid potassium chloride dissolves in water, the temperature falls. Both these reactions occur spontaneously. So this spontaneous, in terms of enthalpy, entropy, discuss the forces that drive reaction. We're talking about, so for NaOH, well, NaH dissolving gives off heat and is exothermic. Its drivers are, well, the reaction is determined by the Gibbs free energy. Delta G must be negative if exothermic, delta H be negative. So delta S must be so minus entropy. Basically, what we're saying is that this value is usually much bigger, so that this value here is, so entropy was not significant, hence delta G negative and spontaneous. Okay. For potassium chloride, however, delta H is positive. So meaning delta, the entropy had to be positive and significant enough to overcome the positive delta H value, as delta G was negative. Because the reaction was spontaneous. So it's just saying that in this second one, that the entropy must have been significant enough to overcome the positive delta H value. All right, and that's it. End of the paper. So nothing we haven't done, but there is a lot there, and you need to practice this type of, you know, being able to, I'm sure when you look at all these questions, it all comes back to you, but practicing it enough that you can recall it when you need to is really the key thing here. You have to be able to have practiced this so that when you're asked a question, the key terms jump out at you and you recognize what you need to do. Okay, thanks.